So today we're going to be talking all about geologic time. We're going to be separating out 4.5 billion years worth of our history, and we're going to cover it in about 2 hours. Well, an hour and a half for today. But we're going to see that throughout human history, we've had very different ideas on exactly how old our planet is. So with this chapter, there are going to be a lot of dates. For the most part, I don't want you to worry about these dates. I'm not going to ask you like what century did these ideas come about in, but I just want you to know what these ideas were and how they changed over time instead. So for most of our human history, we've been trying to figure out our relationship with the Earth. So trying to figure out how we had different landscapes, why the surface of the Earth looked so different in different areas. And especially people were incredibly curious about the Grand Canyon. Here we have over a mile thick rock that has had these really deep valleys cut into it. So they wanted to better understand how these different landscapes formed on our Earth. And at this time, we didn't have any way to actually date our planet. So someone actually went through the Old Testament of the Bible, and there's an entire book in there where it lists people, how old they were, who their children were, and how old their children were. So they went through and just added up all of these ages, and they came up with an age of the Earth that was about 3,400 years old. So that's a really short period of time. So in order to have all these different landscapes forming in just a few thousand years, they believed in this idea of catastrophism, that we had these really gigantic, catastrophic events that were shaping the Earth in really short periods of time. We now know that the Grand Canyon took about 500 million years to form, but they had to come up with a way that this could have formed in less than like 3,400 years. So what they said was that there was this global flood, and that within 40 days, all of the rocks within the Grand Canyon had been eroded so that there were these really deep valleys inside of it. So they were just trying to compress these large-scale events down into these shorter, catastrophic events that could fit up with how old they thought that the Earth was at that time. But a couple hundred years later, we started figuring out more about the different processes happening on our planet. And we kind of gave up on that idea of catastrophism. And instead, we moved forward with this idea of uniformitarianism. Here, everything has been uniform throughout the history of the Earth. And this is in regard to all of the physical and the chemical and biological laws. So think about something like gravity. They thought that since gravity existed at that time, that likely meant that gravity had existed throughout the entire history of our planet. So these laws were uniform. They didn't change throughout the planet. So if it were taking really long periods of time for rocks to erode in that present time, they had to understand that in order for something like the Grand Canyon to form, it would have to take incredibly long periods of time and not just 40 days to form. So the biggest factor behind uniformitarianism is that if we want to understand what's gone on in the past, we have to understand what's going on today. We need to study these natural laws, things like gravity or water eroding rocks, to understand how these rocks were formed in the past. And now they no longer thought that the Earth was only a few thousand years old, but instead they thought it was probably millions of years. And these geological processes happen over really long periods of time that have allowed different landscapes on the Earth to form, not only in different areas, but over different points in our Earth's history. Sorry. So we have two different types of dating when it comes to the rocks on our planet. we're going to have numerical dating, where we're actually going to be able to put a number on how old something is. And we also have something called relative dating. Here, we can't say that this feature is 20 million years old, but instead we're going to list things in a relative order, saying A happened first, B happened second, and then C happened third. So for most of the history of this idea of uniformitarianism, we've had to use this relative dating. We didn't have the technology to actually come up with a numerical age for our landscapes. So instead, we had to rely entirely on relative dating. Here we're just creating a timeline, or kind of like a sequence of events, whenever these different types of rocks started to form. But now we actually have the technology. We can take small pieces of rock and we can put them through an instrument that is going to measure the chemistry of the rock and actually give us an exact numerical age, which is a lot more accurate than saying A happened first, B happened second. So we're going to start off today talking about relative dating, since it's what we've relied on for the longest period of time. And then we're going to end talking about that numerical dating. So we're going to see that there are 6 different principles when it comes to relative dating. So if you've ever done sand art, where you're just pouring in different colors of sand inside of a container, you're going to be layering that sand one layer on top of the next. And this ties in with our first principle called superposition. So here we're just saying that all of the beds, these layers of sediment or rock that are at the bottom, have to be deposited first. As we go higher and higher in this rock sequence, those rocks have to be younger. So think about your sand art. The bottom layer in your container has to be the oldest before you can start burying more sand on top of it. So here with a superposition, again, our oldest beds, or these oldest layers, are always going to be found at the bottom. And then as we work our way up, they're getting progressively younger and younger. And we can see that here at the Grand Canyon. It's just formed up of different layers of sediment that have lithified into solid rock over time. But in order to form these uppermost layers, we had to have formed these lower layers first. The lower layers have to be older due to superposition because we need to start piling on top of it. So if you've never played with sand art, think about constructing a building. If we're going to build a 3-story building, we have to start on the first floor and then work our way up to the third. Physically, we can't start building the third floor and then work our way down to the ground. But our second major principle is related to something called original horizontality. So all layers of sediment are always deposited in this nice flat horizontal position, which we can see here in the image on the left. So if we see rock layers that aren't flat, they're no longer horizontal, they've had to have been disturbed or disrupted at some point after they had been deposited in those flat layers. So if we look at the image on the right, you can see that they've all been folded. That means that all of these rock layers had originally been deposited in a flat layer. And then something happened to disturb them. Now they're suddenly folded into these arches that make up these folded or these inclined rocks. But originally, all sediment has to be deposited in these nice, flat, horizontal layers. And our third principle is called lateral continuity. This just means that the layers were deposited continuously. So think about the Grand Canyon. You can go down to the base and have rocks, entire walls of rocks on either side of you. But the way that these rock layers had been deposited Sorry, my cat keeps bumping into the laptop. The way that these rock layers had originally been deposited were that they were continuous. But over time, something came through, like a river, and it started eroding away in the middle, leading to these deep canyons that formed. So this principle of lateral continuity, if we're missing a giant chunk of rock in between two walls of rock, this likely means that all of those rock layers that were eroded away, it was laid down in one continuous layer before any of the erosion had carved it out. And our next principle has to deal with cross-cutting relationships. Here we're going to see where things are going to cut across rocks. So think about things like faults or an igneous intrusion. Both of these, with a fault, we're breaking rocks, and with an igneous intrusion, we have magma breaking inside or intruding inside of these rocks. So with this principle of cross-cutting relationships, this is just telling us that if we have something cutting through a rock, like a fault or an intrusion, whatever's cutting the rock has to be younger. In order for that rock to be cut, it has to exist first. It has to be older, therefore making whatever's cutting it younger. And somewhat related to this is going to be something called the principles of inclusions. So here it's going to be more about sedimentary rock, those rocks that have little pebbles of pre-existing rocks inside of them. So if I have a sedimentary rock that's full of pebbles that have been lithified or glued together, those pebbles had to have first existed before they could be glued together. So here when we're seeing an inclusion, like a pebble inside of a rock, that pebble has to be older. It has to exist before it can be glued together as a new sedimentary rock, making the entire rock itself younger, and the inclusion, the pebbles inside of it, have to be older. So with all of these principles combined, it means that with our rocks, ideally all the rocks on our planet, at least the sedimentary rocks, they would look all like the Grand Canyon. They would all have these nice flat layers to them. And this would lead to rocks that are called conformable. That would mean that there hasn't been any kind of interruption or pause between depositing different layers of the sediment. But more often than not, we're going to have some kind of disruption. Maybe we're going to stop depositing new sediment. Or maybe the deposited sediment is going to be eroded away in a storm. Either way, we're going to be missing a history of that rock record. We're going to be missing an entire layer of rock. So this is going to lead to things that are called unconformities. There are going to be multiple types of these unconformities, but basically it's just telling us that we're missing a layer of rock. So our first type of unconformity, we have three overall, but our first type is called an angular unconformity, and it's the most obvious type. So here we can see that the actual layers of rocks are going to change angles. Here we can see that the bottom layers are going in one direction, and our upper layers are going in another direction. We're changing the angles of these rocks. So therefore, it's an angular unconformity. This means that at the top of this layer, we had to have some kind of pause in either depositing new sediment or eroding sediment away so that it could go from flat layer to being tilted. And then the top part is just going to be eroded away, and we're going to start depositing another layer on top of it. Anytime that we're changing the angles of our rock layers, it's going to be an angular unconformity. So this one, it's fairly obvious to recognize. We're just looking for changes in the angles. So here, if we look at this image on the right, it may be a little hard to see right now because this is small, but the rocks along the bottom are all completely vertical. And the rocks on top of that are all tilted at an angle. So here we would have this angular unconformity shown by this thin white line. All around this line, we're just missing some part of that rock record. Either deposition had stopped or we eroded away an entire rock layer before depositing more layers of sediment on top of it. Again, we're just changing the angle between two different rock layers. But our second type of unconformity is called a disconformity. And this one is actually really hard to tell because we're going to see two sedimentary layers, one on top of another. And most of the time, they're going to still be perfectly flat. Think about the Grand Canyon. If you've seen pictures of it, it's these very nice, thin, flat layers of sediment that have turned to rock over time. But with a disconformity, we're just missing a layer of that sedimentary rock somewhere in that stack of rocks. So here, it's very difficult to figure out that we actually have this disconformity. The Grand Canyon has a lot of sandstone in it. So we're just going to see two layers of sandstone, one on top of another, still totally flat. But if we look very closely and look for very specific pieces of evidence, we might be able to figure out that a disconformity is present. There was just some time period where there was a lot of erosion, and therefore we're missing a layer of sediment between these two sedimentary rock layers. And our third type of unconformity, and this is the last one, is called a nonconformity. So now we're going to be changing the types of rocks. If we look at the bottom here, we're going to see that these rocks are either going to be igneous rocks or metamorphic rocks. But what's going to be very important to note about these is that these are going to be the igneous and metamorphic rocks that form really deep inside of the earth. But directly on top of these deep igneous or metamorphic rocks, we're going to find sedimentary rocks deposited directly on top of them. So with sedimentary rocks, these only form on the surface. So if we're taking something like a granite, which can form miles underground, and then having something directly on top of it, like a sandstone that's forming at the surface, we know that we have to have an unconformity. We're missing a giant chunk of rock that's separating the granite that formed 2 miles below the ground and the sandstone that formed on the surface. So with these nonconformities, we're looking for changes in rock types. We're always going to see an igneous or metamorphic rock on the bottom, followed by a sedimentary rock along the top. They form in very different environments, so there's no physically possible way that we're going to see them stacked one on top of another unless we're missing a layer of rock between them. So when we look at the Grand Canyon, we actually see all three types of unconformities. When we see an angular unconformity, again, these are pretty obvious. We're just looking for changes in the angles of our rock layers. Our disconformity is going to be the hardest to recognize because we're going to be going from flat layers of sedimentary rock along the bottom to flat layers of sedimentary rock on the top. So here, you're going to need some specialized geological training to figure out that we have a disconformity here. We're just missing a layer of sediment between these two time periods. And then finally, we can have a nonconformity. Here we're looking at a schist. Schist is one of those metamorphic rocks that are really high grade metamorphism. They're going to form really deep under the ground. And then on top of it, we have sandstone, which is forming on the surface. Because schist forms really deep under the ground and sandstone forms really high up on the surface, we have to be missing an entire chunk of time or have a non-conformity between these two rock layers. So when we're relatively dating rocks, we want to be able to go through and figure out kind of like a timeline. What happened first? What happened later on? So with relative dating, we're not coming up with actual dates or years when something happened. Instead, we're just creating a sequence of events, saying this happened first, this happened second. So here, if we start off with part one, we're going to see these layers of sedimentary rock. Using that principle of superposition, layer A had to have formed first. It has to be the oldest because it's at the bottom. So here our sequence, if we were going from oldest to youngest, which is what we always do in geology. We always start off with old, work our way to the recent. So here this sequence of events would be we deposited layer A, B, C, and then E. Again, that superposition. We have to start off at the bottom and then work our way upwards. But if we go from 1 to 2, we'll see that we now have this new layer inside of it. And this is a sill. It's one of those igneous intrusions where we have magma intruding or breaking inside of pre-existing rock. So this tells us that after E had been deposited, which we saw in part 1, then D intruded. It broke inside between C and E and formed a new layer. Can you all see the notes here? Oh, I guess I can't even type them. Never mind, I was going to create a list. So if we're just going to start from the oldest, please ignore my mouse writing. We're going to start off and see that A forms first, then B, then C, oh, that was bad, and then E. But then still D broke inside of these layers. But if we go from 2 to 3, we're going to notice that another igneous intrusion has broken inside. Now this is a dike, and this dike is cutting across all of these pre-existing layers. So in order to cut through all of these rock layers, those rock layers had to exist first. We're going to have the rocks before magma can intrude inside of it. So if we were to see that the sill stopped at D, it would tell us that layer E was actually younger than the sill. Because if E existed, that sill would still break inside of it. But if we go from 3 to 4, we're going to see that the main difference here is that these rock layers are no longer flat. They're not in these nice horizontal layers. Now they've all been tilted at an angle. And between 4 and 5, we can see that we're changing the angles between these rock layers. At the top of E and then going into G, we're going from tilted up to flat rocks. So here we have one of those unconformities. Not going to spell that out. So just an unconformity is present there. And then we're going to start depositing on top of it. And again, with that superposition, we're going to see that G starts first, then followed by H, etc., with I, J, and K. So with these relative dating principles, we just want to start off with our oldest layer, usually at the bottom, and then work our way up to the youngest layer, figuring out what formed when. So now we're going to talk about my favorite part of this chapter. I would be handing out fossils if we can meet face to face, because here I think this is probably one of the most interesting parts of our entire semester. So fossils, it's just the remains of some kind of ancient life form. We generally think about things like dinosaur bones, but most of the time we're going to see things like a mold. We're going to be able to see the shape and what the surface of either that plant or animal looked like. And if you were to study fossils, you would just be called a paleontologist. I know, at least for me, the first time I saw any of the Jurassic Park films as a kid, I instantly knew I wanted to study fossils. So those films have spread a lot of light on people wanting to study geology. But we're going to see that fossils can come in a lot of different forms. Again, just finding those entire bones are actually fairly rare. So today we're going to talk about 6 fossils that are actually common and how they form in different ways. So we're only going to talk about 6 possible ways that a fossil can be preserved, but there are tons of different ways. We're just going to stick with some of the most common types. But we're going to see that not all plants or animals are going to be preserved, and other plants and animals are going to have a better chance at being preserved. So think about a jellyfish. If I had a pet jellyfish that died and I decided I wanted to go bury it in my backyard, once I dig the grave for my jellyfish and I place it in the grave and start covering it with dirt, because it's so soft, it's full of water, when I put more dirt on top of it, eventually it's just going to squish my jellyfish. So we see that things that are really soft, we don't get a lot of fossils forming from them. Instead, most fossils are forming from hard parts, things like teeth, bones, and shells that are going to be able to stand up to the weight of all the sediment on top of them. If I bury a bone in my backyard, it's unlikely that it's going to be squished. It's just going to be covered in dirt. And for the most type, we're only seeing that parts of our plants or animals are being preserved, not the entire thing. But there are some really weird, kind of cool exceptions. So one of these are these frozen woolly mammoths. I believe it was in Siberia in the mid-2000s. They found a small herd of woolly mammoths that had been stuck in ice for over 10,000 years, and they were perfectly preserved. All of their body parts were there, down to all of the fur covering their body. They had been so well preserved that you could even buy a woolly mammoth steak for like $20,000 and eat it. Turns out it was really gross. I wouldn't eat something that's been frozen for 10,000 years. But it was really cool because we rarely ever see these entire animals being preserved. And the only other one I could really find were these mummified sloths. Sorry for the typo on this page, a sloth. It was found in a really dry cave in Nevada. So we're going to see later on that oxygen is really important when it comes to decay. So if we're in a really dry cave, that means that there's not going to be a lot of water or oxygen in the air. So it led to these sloths, their entire body down to their fur being preserved. But again, this is super rare. Most of the time, we're just going to find parts of these plants or animals that are being preserved as fossils. So the 2 most common types of fossils we see are things that are either petrified or molds. So the scientific name for petrified is permineralization, but I prefer petrified because the word itself literally means turned to stone. Think about that old myth of Medusa. If you actually saw her and her little snake head, you would instantly be turned to stone. You would be petrified. And we can see fossils developing this way. Most of the time, it's going to be wood that's going to be petrified. We're going to have something that's going to fall into the water. And we know that water is rarely ever pure. There's always minerals dissolved in our water. So over time, each individual cell of this wood is going to be transformed from wood into solid stone. It's going to turn into silica or quartz. So over long periods of time, this is no longer going to be a chunk of wood. It's going to be a chunk of silica that looks and feels exactly like a piece of wood. But now the main difference is that it's no longer wood, and it's going to be incredibly heavy. If I could pass around a piece of petrified wood for you, you would notice instantly when you hold it that it's probably at least 10 times as heavy, because now it's solid stone instead of just a lightweight chunk of wood. But our other really common types of fossils are called molds and casts. So both of these, it's just going to tell us what the outside shape and what the surface of these plants or animal look like. We're not preserving the entire animal. So here we can see an insect that was preserved, but it's just telling us what the shape and what the surface looked like. None of the internal parts of this animal were actually preserved. So with a mold, think about an ice cube tray. You're going to pour in water, stick it in your freezer, and then a few hours later, you're going to be able to pop out a piece of ice. That ice is going to take on the exact shape and surface of your ice tray mold. But the other really common type is called a cast. This is where the outside is going to be covered with something, and then whatever's inside is just going to be removed away. So think about if you've ever broken a bone and had to get a cast. Once your limb heals and that cast is cut off, even though your leg or your arm is no longer inside of it, as long as you keep that cast, you're going to have a perfect preservation for what your arm looked like, what the shape of it was like, what the size of it was like, even though your arm itself wasn't preserved. So these three, petrification, molds, and casts, are actually our most common types of fossils. But we're going to see other types that develop as well. And with these two, with carbonization and with amber, these are going to lead to incredibly detailed preservations. So with carbonization, it's going to result in a thin film being left behind, showing what the surface of an animal looked like. And here we can see the film of a bee. So think about like old school cameras that relied on film. The film in those cameras were incredibly thin. And that's the same way that these carbonization fossils are. We're talking about fossils that are thinner than a sheet of paper. So they're going to be incredibly delicate and easy to break. But they're going to give us a whole lot of detail about what that animal looked like. If we look at this bee, we not only instantly know that it was a bee, but we can see all the details down to the different little folds inside of its wings. So these carbonization, these carbon films, they're super delicate and easy to break, but they're also going to show us a great amount of detail of what the surface of that animal looked like. But another one with great preservation is called amber. Amber forms basically from the resin or the sap of ancient trees. And we're going to see it happening a lot around volcanic eruptions. When volcanoes erupt, they're going to release a lot of heat. Therefore, this heat is going to force all the resin out of the trees. So whatever was currently sitting on that tree is basically going to get stuck in resin, kind of like a super thick syrup, and it's not going to be able to escape. But as that resin starts to cool off, it's going to harden, and it's going to trap everything inside of it, sealing whatever is inside of the amber off from the atmosphere and from water. And this part is what's important, because both our atmosphere and water have oxygen inside of them. And if we want to preserve something fairly well, the best thing that we can do is remove all of the oxygen so that it doesn't break down over time. So think about if you were to get like in a small fender bender in your car, and you just decide to never get that dent fixed. Over the next few years, The oxygen in our air and in our water is going to cause your car to rust. It's going to start breaking down the surface of your car. And we see this happening with living things as well. So it's really important here that these animals that get trapped in amber, they're completely sealed off from oxygen. And it's going to lead to great preservation. If we could zoom in on this spider, we would be able to see each individual piece of hair on its legs. But everything we've talked about so far has been a body fossil. Fossils that are telling us about the body of a plant or an animal. But not all fossils tell us about the body. Sometimes it's just going to tell us that an animal was there. So some of the really common types are going to be tracks. Think about like footprints. If you were to walk in a muddy area, leave your footprints behind, and then eventually that mud is going to harden and turn to stone. We might not ever figure out exactly what kind of animal left those tracks, but we can figure out a little bit about the behavior of that animal. Did it walk on 2 legs or on 4 legs? We can figure out how tall it was based on how widely spaced the feet prints are. If they're really close together, it's probably a really small animal. But if they're really far apart, it's probably a lot taller and bigger animal. But another really common type is called a burrow. So think about the animals outside in your yard that are constantly burrowing or just digging through the ground. They're going to leave these tiny little tunnels or hole system behind. So again, we might not ever know what was digging in the sediment before it turned to stone, but we know that there was some kind of life that was burrowing and creating these tunnels in the sediment. And then here at the bottom, this is my favorite trace fossil. This is called a coprolite. This is fossilized poop. Again, we're not going to know what kind of animal left it, but it can tell us a little bit about the diet of that animal and especially the size of it. So if you could see this entire ruler, this coprolite or fossilized poop sample is 6 inches wide. That means, at least I hope, that it was an incredibly large animal that left this dung behind that eventually was cut off from oxygen and was preserved as a fossil. But we're going to see that only a really small amount of all living plants and animals will ever be preserved. It's far less than even half of a percent. And that's because we need some very specific things to happen in order to increase our chances of having these organisms being preserved as a fossil. So the first thing is that we just need to rapidly bury it. We want to cover it with as much dirt as quickly as possible so that we can cut that organism off from the oxygen in our air and in our water. So if we can very quickly cover it in 10 feet of dirt, it's very unlikely that oxygen is going to make its way down to that organism and decay it away. But we're also going to see that hard parts, things like our teeth and our bones, are going to be better at being preserved. And that's because our soft parts are really easily decomposed. If I were to die and be buried outside, the fat on my arm, it's going to go away really, really quick. Probably within a few months, the soft tissues in my body are going to decompose, but my bones are going to remain there for years. And we also see a lot of animals like vultures that will go around and they'll eat these dead animals. So they're helping decrease the chance of things like tissues and muscles being preserved. But we see that these hard parts, again, like our teeth and bones, or even simpler animals that have shells, here they're going to be much more likely to be preserved. Because when we bury them under sediment, we're going to be protecting them from oxygen. And nothing really eats bones or shells, so we don't really have to worry about these hard parts being ate either. So we see that our fossil record is very biased. Animals that are really soft, again like a jellyfish or a worm, they're rarely ever preserved. Most of the time, we're going to find these hard parts, these shells and the bones that have been turned into fossils. So now we're going to try to bring together our first and our second major points of this chapter. Those ideas of relative dating and our new knowledge about fossils. So we want to be able to correlate. We want to be able to match up rocks in different areas. So again, think about that principle of lateral continuity. If we're at the Grand Canyon and we have two layers of rocks on either side of us, we want to be able to match up the rock layers going between them to say that they all formed originally in these nice, flat, horizontal layers. So this correlation is just going to give us a much better idea of how these rocks were deposited and preserved over time. But sometimes there's going to be a large area separating these layers of rock. So it's not always going to be the Grand Canyon where it's just 10 or maybe 100 feet separating these rocks. Sometimes they can be entire states away. So we're going to need to look at the specific types of rocks. So that it's like shale, sandstone, and then another layer of shale. If we go a few miles down the road and we can find that same pattern of shale, sandstone, shale, it's likely that those were once forming at the same time. But if we can find fossils inside of those layers, it's going to help us narrow down those time frames in which these rocks actually formed. And that's because fossils are only going to be preserved at the time that these plants or animals were actually alive on the earth. So if I find a rock with a dinosaur fossil inside of it, I know that that rock had to have formed at some time when the dinosaurs were around. There's no way that that rock formed last year because dinosaurs have been extinct for millions of years. So to do this, we're going to use our last principle called principle of fossil succession. And this is because there's been a definite order of when new plants and animals evolve and when other plants and animals go extinct. So we basically created this timeline of when animals evolve and then when they go extinct so that we can know exactly when they were around on our planet. So again, if I find a rock with a dinosaur bone, I know that it had to form millions of years ago. But if I find a rock with a human bone inside of it, humans have only been around for about 100,000 years. So I know that that rock had to have formed in the last 100,000 years. There was no way that it formed a billion years ago because humans had not yet evolved at that time. So if we look at the fossils in our rocks, on top of those previous principles of relative dating, we're not only going to be able to create a sequence of events, saying this happened and this happened, but we're going to be able to narrow down the time frame when those rocks could have formed. Excuse me. And to do this, we need to use something called an index fossil. So with these are going to be very specific types of plants or animals, where geographically they're going to be widespread. They're going to be found not in very limited areas, but throughout entire continents, and sometimes multiple continents at once. But what's most important about these index fossils is that they're only around on our planet for a really short period of time. Some of them might be around for just 100,000 years, like humans. So if we find these index fossils in our rocks, and they've only been around for a short period of time, it's going to be really easy for us to narrow down when that rock formed. We would have to know that it formed in that very short span of time that that plant or animal was around. But our fossils are also going to be really important for helping us figure out what kind of environment that these fossils formed in. So, for example, if I find, let's say, a T-Rex fossil, I know that that fossil had to form on land because T-Rexes didn't live in the oceans. Here we can see coral. coral is a really good index fossil because, like us, our species, coral is a relatively recently evolved animal. But coral is also going to tell us about the environment. If we find fossilized coral, we know that it had to have formed in a warm, shallow sea, like what we see not only around Florida, but throughout the equatorial region of our planet. We're not going to find corals growing in the middle of Kansas or in really cold polar waters. So these fossils are going to help us narrow down not only the time that these rocks could have formed, but sometimes kind of very generally the environment that they formed in as well. So here we're just looking at a stack of rocks. We have rock unit B at the bottom, rock unit A at the top. So just based on that principle of superposition, we should automatically be able to figure out that rock unit B has to be the oldest because it's found at the bottom. In order to have stacks on top of it, rock unit B had to form first. It has to be the oldest. But when we look at this, we're going to see that there are some common fossils between these two layers. So we can see that there are clams here on both layers. Now if we look at the right, this is just a diagram showing us how long of a time have these plants or animals been on the planet. So if we look at this clam, we can see that they've been around for a really long period of time. So they would not be an index fossil. With index fossils, we want them to be around for a short period of time. So instead, the index fossil for rock unit B would be this, which is called a trilobite. I like to lovingly refer to it as the ancient cockroach. It was found everywhere and in huge amounts of numbers. And it was only around for a really short period of time. So here we can see that the trilobite was around for a lot shorter of a region of time than this clam was, making it a good index fossil. And if we look up at rock unit A, we can see a dinosaur skull. Here, dinosaurs have been around for a short period of time. So both of these, the trilobite, that ancient cockroach, and the dinosaur, these are our index fossils. They're going to be really widespread and found over large areas, but they're around for a really short period of time, which is going to help us narrow down roughly when those rocks started to form. So that was relative dating. Even when we're using those index fossils, we're just creating a narrow range of when those rocks could have formed. But when we're talking about radioactive dating or numerical dating, here we're going to be very precise and specific on exactly how old those rocks are. But this radiometric or numerical dating, it has a little bit of chemistry involved. So I'm just going to spend a second going over a little bit of review about what our atoms look like. So in our atoms, we're going to see that in the center of our atom, we're going to have the nucleus. Inside of the nucleus, we're going to have protons and neutrons. Protons have a positive charge, and the neutrons have a neutral charge. They don't have any charge whatsoever. But outside of our nucleus, we're going to have rings of electrons that form. And these electrons have a negative charge to them. So if we're trying to figure out what kind of element we're looking at, when we're looking at our atom, we want to know how many protons are inside of that nucleus, which is called its atomic number. If we start changing the number of protons, if we add one or take it away, we're going to be changing a lot about the weight and the charge of that atom. So if we take carbon and we add one proton to it, we're going to be changing that element. It's no longer going to be carbon, but it's going to turn into nitrogen instead. And we're going to see that almost all of the mass, all of the weight and the space of an atom is found in the nucleus between those protons and neutrons. The electrons are outside of the nucleus, and they are incredibly tiny. They also weigh almost nothing. So when we're talking about the atom's mass, we don't even care about those electrons because they're so small and so lightweight. But if we take the number of protons and the number of neutrons, both of these particles that are found in our nucleus, this is going to give us the overall mass of this atom. But while we can't really change the number of protons in an element, we can change the number of neutrons. This is not going to change the element or its charge. It's just going to change the mass. And this is going to lead to something called an isotope. An isotope is one element that just has different masses because it has different numbers of neutrons. So here we're looking at two isotopes of oxygen. If we look closely, we'll see that the one on the left has 8 neutrons, while the one on the right has 10 neutrons. Because the one on the right has 2 more neutrons, it's just going to have a higher mass. It's going to weigh more and take up a little bit more space. Because it has a higher mass, it's going to cause this atom to behave differently. Think about 2 people. One person weighs 150 pounds. The other person weighs 600 pounds. They weigh more and they take up more space. They have a higher mass. Because of the changes in their mass, they're going to behave very differently from one another. That 150-pound person is probably going to have a lot of energy. They're going to move around a lot. Whereas that 600-pound person that has a lot of mass to their body, they're going to have very little energy. They're not going to have enough energy to get up and do most basic things in their life. So they're not going to travel very large distances. So we're going to see that isotopes have different masses to them. The lighter an isotope is, the more energetic it is. It's going to be moving around. But the heavier that mass is, if we start adding on more weight to this isotope, now it's going to start getting a little sluggish. It's going to start moving around very, very slowly. So some isotopes are stable. That means that they're not going to change over time. But a lot of isotopes are radioactive. This means that they're unstable, and they're going to decay constantly. So with these isotopes, they always want to change from an unstable isotope and become more stable. You are probably like me, and I decided to go to college so that I could be more financially stable later on in my life than my parents were. And this is going to have a lot of wording that's similar to how these isotopes decay. We're always going to start off with an unstable parent. It's just going to have bonds inside of its nucleus that are weak. It's not going to be able to hold all those protons and neutrons together. So the more energetic or the lighter that isotope is, those particles in the nucleus are just moving around like crazy because they're lightweight. So over time, the nucleus is just going to start breaking apart. It's going to lose parts of its, either generally it's neutrons or protons. But as it decays and it gets rid of some of these particles, it's now becoming more stable. The bonds are going to be able to hold those protons and neutrons together. And therefore, it's going to end up being more stable, in which we call the daughter isotope. So with these, we always go from an unstable parent isotope that's going to decay into a more stable daughter isotope. I am so sorry, y'all. I just realized that it's 4:30. You guys should have let me know about the time. So I'm really, really sorry that I went so far over today. Wait, what time do we get out? Oh, okay. Never mind then. I thought we got out at 4:15. It's like, wow, you guys are into this today. Uh, so never mind then. We still have plenty of time to keep going then. So with radioactivity, there are 3 types. But this is not a chemistry class. I don't want you guys to worry about memorizing these three specific types of radiometric decay. What I want you to know is that we always go from an unstable parent isotope, where the bonds can't hold everything in that nucleus. We're just going to kick something out. And now that nucleus is going to be stronger. Now it is decayed into a more stable daughter isotope. So in the last 60 years or so, we've started being able to not only relatively date rocks, but we can also radiometrically date them. We're going to be able to take small samples of these rocks, send them through an instrument, and it's going to pop out an exact year. You might be able to say that this rock is 1.2 million years old. So it's going to be a very precise numerical age for these rocks. So it's just a whole lot more reliable. And the way that we have figured this out is because this radioactive decay, if we're looking at one specific isotope, the amount of time it takes for that decay to kick out those unstable parts doesn't change for each element. It constantly stays the same. And we've been able to really precisely measure how long it takes for that unstable parent isotope to kick out the unstable part. So we're going to see that rocks are going to be forming, and as they start aging, we're going to start seeing the ratios or the amount of parent and daughter isotopes changing over time. And this is because isotopes, these radioactive isotopes, have something called a half-life. And this is just the amount of time that it takes for one half of the nucleus to decay. So we're going to have, let me see if I can do this through the notes. Oh, it's not going to let me leave. So I'm just going to create my own notes. I'm going to give this a shot. Hopefully you'll be able to read it. And if not, I'll just create a table and upload it. Okay, so we're going to start off with a rock that just formed. So let's say that it's an igneous rock, and today is the day that it's solidified from lava and turned into a solid. That means at that point, we're going to have 0 half-lives going on. That means that if we were to look at every single atom inside of it, that 100% of those atoms are going to be those unstable parents, meaning that 0% of the daughter has formed yet. Because again, that rock only formed today. But let's say that a half-life goes by, just the amount of time it takes for half of these parent isotopes to decay into our daughter isotopes. Now, instead of having a 100 to a 0% ratio, now because half of our parents have decayed into the daughter, after one half-life, we're going to be at a 50-50 ratio between the two. If we allow another half-life to go through, now 2 half-lives have happened. After one half, we were down to 50% of our parent. But now we're going to lose half of that again. We're going to be down to 25% of the parent, and then 75% of the daughter. And this is just going to keep going on and on. So after 3 half-lives, we're going to be down to 12.5%, and then 87.5%. So here, with each half-life, again, we're always losing half of our parents, and they're being decayed into those more stable daughter isotopes. So if we know exactly how many half-lives have passed, if we can measure the ratio of how much parent to daughter there is in that rock, we can figure out exactly how old that rock is. So let's say that we find a rock where there's that 25-75 ratio, where it's 25% parent, 75% daughter. This ratio will tell us that two half-lives have happened. So if the half-life of that isotope, let's say it's 100 years, if two half-lives have gone by, then that rock is going to be 200 years old. But for each different isotope, the half-life is going to have very different amounts of time it takes for half of those parents to decay into the daughters. Some of them have super long half-lives. We look here at uranium-238. Its half-life is as old as our planet is. So this one would be something good if we're trying to date the age of the universe, something that's older than 4.5 billion years. But overall, you can see that there's a big range in the amount of time, and each individual isotope has its own half-life. And most of these isotopes, we've been able to really precisely measure that half-life. So this is a super wordy slide. I really only want you to focus on the first two parts. Since we've had this technology develop, we've been nerding out. We've been dating all the rocks that we can possibly find on our planet. And every single continent, we've found rocks that are at least 3.5 billion years old. So this really throws out that idea of catastrophism. Now we really know that the Earth is not 3,400 years old. We know that it's at least 3.5 billion years old because we found these rocks on every single continent. But the oldest rocks that we've ever found were found in Canada. And these rocks were just about 4.3 billion years old. We know that our planet itself is 4.5 billion. So here we're missing about 200 million years worth of rock. We've never been able to find a rock that formed on the Earth that's 4.5 billion years. And we'll talk about this in the last few slides, but that's because when our planet first formed, we were just a giant ball of magma floating out in space. We were so hot that we didn't have any rocks on our planet the first couple 100 million years. And at this point in time, this is called the Hadean period. Hadean, like Hades. We were just a giant ball of fire and magma spinning out in space. So we actually don't have rocks from when the Earth first started forming. But we have found rocks that are at least about 4.3 billion years old. But probably the most common, at least the most commonly used in just a normal setting, kind of radioactive dating is radiocarbon. If you watch any documentaries where they're talking about like archaeological sites, they talk a lot about carbon-14, which is this radioactive isotope. But here it has a really short half-life of like 5,700 years. If I were looking at like a Native American tool, I wouldn't want to date that with something that has a billion-year-old half-life, because we know that humans have only been around for about 100,000 years. So looking at radiocarbon, or carbon-14, because it has a short half-life, it's going to be incredibly useful in looking at things from our recent past, especially our recent human past. So we're going to finish up today just talking about our geological time scale. So our Earth's history, 4.5 billion years is a long time. And it's kind of hard to at least even wrap your mind around how many zeros and how many years that really is. So in order to make things a little bit better to comprehend and kind of wrap your mind around, scientists have created a geological time scale. They've broken down this huge history of our planet down into more manageable periods of time. So our largest spans of time, we're going to break things down into eons. So we're going to have two different eons. The first one, which takes up almost all of the history of the Earth, going from 4.5 billion years ago to about 540 million years ago, is called the Precambrian period. And we'll talk a little bit more about that one in a minute. But from about 540 million years ago to today, we've been in the Phanerozoic eon. Here, this is the eon that we know the most about. Time-wise, it's a very limited amount of time, but this is where we have most of our fossils that have been formed. But even with this eon, even the shorter one that's only, almost 550 million years, that's still a giant chunk of time. So we're going to break these eons down into smaller eras. And here the wording is going to be important. So zoic just means life. So this Phanerozoic, the period that we're currently in, we're going to break that down into 3 different eras. The first one starting 540 and ending about 250 million years ago is called the Paleozoic. Paleo means ancient, so Paleozoic just means ancient life. Following this, we have the period called the Mesozoic. Mesozoic means middle, so here it's just the middle life. And currently, we're in the Cenozoic, which means recent life. And here we're going to see that the boundaries between all of these different eons and eras is just going to be boundaries between massively different types of life forms. We're going to see that the end of each era, we're going to have a mass extinction. So, for example, at the end of the Mesozoic, not only did the dinosaurs go extinct, but so did about 90% of all plants and animals living on both land and in the water. When we see mass extinctions, it's going to open up a lot of ecological space for new animals to evolve. So the Mesozoic ended with a mass extinction. But the Cenozoic, the period we're currently in, started with massive evolution. The Cenozoic is best known because this is when mammals evolved. And eventually, those mammals are going to evolve into humans, into us. So we're going to see that with each mass extinction that's going to end an eon or an era, it's going to bring in a new eon or an era that's starting off with just massive evolution. Totally different types of plants and animals are going to develop. But even with these eras, we're still talking about giant chunks of time. And these are broken down into periods, and the periods are broken down into epochs. But for here, I just want you to know the eons and the eras. I want you to know the 2 eons are the Precambrian and the Phanerozoic. And then that each of these are broken down into 3 eras. But here, I'm not going to ask you specifically about ages, when they started and when they stopped. I just want you to know Paleo, ancient life, Meso, middle life, Ceno, recent life. It's going to tell you which order that they occurred in. So, even though most of our history, or at least what we know about, is from this Phanerozoic, from today back to about 540 million years, that's only a tiny chunk of our life as a planet. That means that we're missing about 4 billion years worth of material. And all of this period is called the Precambrian. Here, this is a gigantic chunk of the history of our planet. And it's over 88% of our history. But during our Precambrian, here we had very basic forms of life. We didn't have things that had any types of hard parts, not even shells. So we have very few fossils from this Precambrian period. But with our Precambrian, we're going to break it down into 3 eons. The first one that's not listed is that Hadean. That was here the first 200 million years before the Earth started cooling down and rocks actually started forming at the surface. So again, just Hadean. Think about Hades, balls of lava and fire just covering the entire Earth. But once the Earth cooled off and started forming these solid rocks, we started seeing that really basic forms of life started to develop. Nothing complex, mostly like bacteria and algae, mostly single-celled organisms. But because we're having life evolving, that brought us in to the Archean eon. It's very, very basic life, but we've still had new life evolve. But at the end of the Archean, we started seeing evolution, and animals started getting slightly more complex. Still nothing with a hard part, but instead of just having single-celled organisms, now we're starting to see things like worms develop. They're still entirely soft, so we don't have a lot of fossils, but they're slowly getting more and more complex. But Proterozoic, think about prototype. It's just like your first draft or your first form. At the end of this Proterozoic, we had a mass extinction where like 97% of all life on our planet, both in land and on water, or in water and on land, went extinct. This led to massive evolution. And now we're starting to get complicated animals. We're starting to get animals that have shells and bones inside of them. So at the beginning of this Phanerozoic, we started seeing a lot of fossils being preserved. So with our rocks, we can't radiometrically date all of them. That's because of those inclusions. Think about sedimentary rocks and how they are mostly made out of particles, these pre-existing rocks inside of them. So if we were to take a sedimentary rock that has a bunch of pebbles inside of it, and we were to date the age of the pebbles, it would tell us a really incorrect date because those pebbles had to exist before they could all be glued together as a new sedimentary rock. So we're going to see that radiometric dating, or that numerical dating, only really works well for igneous and metamorphic rocks. If we try to do it with a sedimentary rock, we're going to get an age that's way older than the rock itself, because we would be dating the particles that have all been glued together as a new rock. But a lot of the rocks on the surface of our planet are all, well, a good chunk of them are sedimentary rocks. So we still want to be able to kind of narrow down the dates that these rocks formed. So to do this, we're going to combine relative dating for our sedimentary rocks, and if any igneous or metamorphic rocks are present, we're going to look at their actual numerical age to help us narrow down a range that these rocks could have formed. So, for example, here we're looking at the Grand Canyon, which is made up of a lot of just different forms of sedimentary rocks. So if we look at, let's say, the Morrison Formation here near the bottom, we're going to see that it's underneath this volcanic ash layer, this layer of igneous particles. Due to that principle of superposition, we know that this Morrison Formation has to be older than the ash layer on top of it. So although we don't know the exact age of the formation, we know that it's at least 160 million years old, because it's farther down in that stack. Here we can also see an igneous intrusion. We have a dike that's cutting through these rocks. So let's say that we just look at this Dakota sandstone. It's sitting on top of this ash layer. So we know that it has to be younger than 160 million years. But we also have this dike cutting across it. Now, because something has cut into this rock, we know that the rock has to be older than whatever cut it. So even though we can't figure out an exact age for this sandstone, we know that it had to form sometime between 66 and 160 million years ago, because it's on top of that ash layer and it's been cut through by that 66 million year old dike. And then finally, if we go to the very top here, if we go to the Wasatch, we can see that the dike does not cut through it. So therefore, this Wasatch has to be younger than the dike. It wasn't there when it was cutting through all of these rock layers. So again, we don't know an exact age for this Wasatch Formation, but we know that it has to be less than 66 million years old. So most of the rocks on our surface, we're not using just relative or just numerical dating. We're going to be combining them. And a lot of the time, we're just trying to narrow down an age that these rocks could have possibly formed.